Let's go into the class. Great. So let's go into the class we have for today. I hope you understand what I just explained. No. So today we are going into several topics. We're going to look at representation of vectors now. Then we'll look at the vector cross product, a vector dot product, vector cross product, and the rest of this. Now, here is the issue. Now, I'm going to represent all of these features. I will take 4 features now, right? And I'm going to represent them as a matrix. Then I will take the feature, the output variable. All these are input variables. Then I'll take the output variable and represent it as a vector. So let me show you what I'm talking about. So this is how this looks like, right? So our first variable is passenger, right? So let me call it P. I'll take the first five training sets. So I have 1, 2, 3, 4, 5. This is going to take some time, right? So please, you are going to need to hang on. So this is 1, 2, 3, 4, 5. The next one is P class, right? So I'll call it PC. This is our second feature variable. Right? So this is 3, 1, 3, okay, 3, 1, 3, 1. So this is 3, 1, 3, 1, 3. Age, let me use age, right? So age, I'll call that A. And that's 22, 38, 26. 22, 38, 26. Then this is 35, 35. So 35, 35. Sex now. Let me do sex now. I'll call it gender. Now I'm not going to use male and female. I'm going to say male is 1 and female is 0, right? Because that's what we do in machine learning. So this will be 1, 0, 0, 0, 1. So this is 1, 0, 0, 0. What's this? 1, 0, 0, 1. I don't know what's hanging. 1, 0, 0, 1, right? So 1 is for male and 0 is for female, right? So let's just take four feature variables, and then the last variable is going to be our output variable. And that's survived. That's our target variable, our output variable. So 0, 1, 1, 1, 0. So survived now, which is our target variable. 0, 1, 1, 1, 0. So what this means is that this person on the first training set, this person did not survive. The next 3 people survived, and then the 5th person did not survive, right? So we want to use all of this, the data. What's this? What's happening here now? So we want to use all of the data here, right? To determine, to build a model that tells us whether a random or an hypothetical traveler is going to survive this are Titanic ship or not. So this training set is a matrix, right? So this training set is a matrix. So we have 1, 2, 3, 4, and 5. We have 3, 1, 3, 1, 3. We have 22, 38, and so on. Then we have 1, 0, 0, 0, 1. Okay, let me just write it out. 26, 35, 35, right? This is a 5 by 4 matrix, right? Because that's 5 here and 4 here. So this is 5 by 4 matrix. Now, the target variable, which is the survived or not, is a vector. So this is the matrix M, right? This is a vector V equals to 0, 1, 1, 1, 0. So this is a 5 by 1 vector. Does this make any sense to you? Because we've been doing matrices, vectors, and you must have been wondering, what are we doing with matrices, or what are we doing with vectors? Why are they important? Because what happens when machine learning starts, right? Because the processes, when you kick in the algorithms you are going to build later on, you're not going to see them with your eyes, right? But you need to have an intuition into what is happening. So your feature variables are basically a matrix, right? And then your target variable is a vector. That's how to look at it, right? So if you understand that, I would then need to go into, the beginning of today's class, which is just basically matrices and vector.
I don't quite understand.
What do
like you getting the vector out of the matrix?
I'm not saying you're getting the vector out of the matrix. I'm saying that your feature variables, which is your input, is a matrix, and your output variable is a vector.
Oh, okay.
As simple as that. Any other question? Okay, nothing of any question. Let me just go into a new slide, right? So today, right, number one topic is representation of vectors. So I have 2 hours. So after 1 hour, this class is going to end. So I'll just send a new link to the group, and then we'll continue from where we stopped. So representation of vectors, just so that you have a 3D representation of vectors in your head. After today's class, I don't want to come back into anything I've taught on vectors or matrices. Right, so let's say we have a 3D plane like this, a 3D plane like this, right? This is vector Z. Let's say we have another 3D plane like this, right? This is 3D, that's why I'm making it this way. And then we have another 3D plane like this, right? So this is vector. This is vector X. This is vector Y. You can draw this better on your notes, but it's harder for me to draw on my laptop until I get a touchscreen laptop. This is vector Y, and this is a vector Z, right? So let's see how we can represent a vector A. Let's see how we can represent a vector A. Which is equal to 2, 1, 3, right? Of course, you know that this 2, 1, 3 means it's 2 on the x-axis. It's 2 on the x-axis, 2 on the 1 on the y-axis, and z on the 3 on the z-axis. So what do? We just first label our axis. This is 1, this is 2, for example, and this is 3. On our y-axis, we have, let's say this is 1, this is 2. Don't need more than 2 on the y-axis. And then on the x-axis, this is 1, this is 2, and this is 3. Right? So we have x on the y-axis. Sorry, 2 on the y-axis, which is this, right? Which is here. We have 3 on the, okay, sorry, let me do y first. We have 1 on the y-axis. So this is going to be like this. This is 2 on the y-axis, and then 1 on the x-axis. 1 on the y-axis. Then we have 3. We have 3 on the z-axis. Let me clean this up. So we have 3 here, and we have 1 here, and we have 1 here, and we have, right? So this is how you would be able to represent this on, oh God, this is very hard to draw on my laptop. Let me try again. I mean, does anyone know where I'm going? Just try to connect the dots and you'll be able to give it a good representation, right? So I'm going to have this here, which is going to be connected to this. Going to be connected to this, right? So this is how my vector 2, 1, 3 basically looks, right? A 3-dimensional vector. So this is going to be the direction of my vector. This will be the direction of my vector. Does this make any sense to you? I mean, I just want to give you a visual representation of how vectors look like, right? So this is how I've shown you a representation of how 2D vectors look like, right? Just 2 dimensions, this. But this is another visual representation of how a 3D dimension looks like, right? Does that make any sense to anyone? Were you able to draw it on your book, on the plane, and see how it makes sense? So if there's no question on that, the next thing we'll be looking at is vector addition, right? Vector addition, which is as simple as possible. This is the easiest vector operation you would ever carry out in your life. So let's say we have a vector A. We have a vector A equals to 2, 1, 3. And then we have a vector B equals to 5, minus 2, and 0. So what will be the combination of vector A and vector B? Anyone? Anyone? Combination of vector B. So what we just do is we add what is on the x-axis together. We add what's on the y-axis together, and we add what's on the z-axis together. So vector A plus vector B will give us 2 plus 5. That's 7. 1 plus minus 2. That's 1 minus 2. That's minus 1. And 3 plus 0 is 3. So that's the combination of vector A and vector B. Very, very simple. Just add whatever you have on equal planes. So this is the x plane, this is the y plane, and this is the z plane. Add them together, you have your vector addition. Does that make sense? I need feedback. Oh, this class is too dull. Vector scaling. Let's look at how to scale a vector. Let's call it vector scaling. I remember I did something. I taught you guys vector scaling in the last class. Someone has left. I remember I taught you guys vector scaling in the last class. So for example, we have a random vector A. I mean, vector scaling is just multiplication of a vector by a scalar quantity. So for example, we have 3 times vector 2, 1, 3. Right? So just multiply 3 by everything. So we have, this is going to give us 3 times 2, that's 6. 3 times 1, that's 3. And then 3 times 3, 9. So we scaled this vector in 3 places. That's just basically what vector scaling is. It's the multiplication of a vector quantity by a scalar quantity. So this is a vector. This is a scalar. Another example, let's say we have 2 times vector 5, 4, 8, right? I mean, this is the easiest vector operation you can carry out in your life. So this is going to be 10, 8, and 16. Easy as it can get. So multiplication of a scalar quantity, right, by a vector quantity is just what you call vector scaling, right? So if we add a vector 2, 2, for example, so there's 2 on the x-axis and 2 on the y-axis. If you scale it by 3, we're going to have vector 6, 6, which is going to be this multiplied by 3. So if we check out here and here, we're going to have 6. We're going to have 6. Does that make any sense? I need feedback at this point. I need feedback. So I don't want anybody to say, oh, what you explained in the previous lecture, I don't understand one thing. Do you understand it to this point? I bet everybody don't log out now. I need feedback. Oh.
Yes, I understand.
All right, great.
I understand.
All right, great. So the next topic is vector dot product. And this is very, 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 so it gets complex from here, right? It gets quite complex from here. So let's say we have 2 vectors. We have 2 vectors. Vector A is equals to minus 4, 2, and 1. And then we have vector B equals to 3, 1, 3. Now write this down. A dot vector product is going to give you a scalar quantity, right? So we are saying 4 minus 4, 2, and 1. Then there's a giant dot in the middle. Right? There's a giant dot in the middle, right? We're having dot product of this to 3, 1, 3. So let me show you how to calculate a dot product now. So we're going to say 4 minus 4 times 3 is going to give us minus 12. Minus 12. 2 times 1 is going to give us 2. And then 1 times 3 is going to give us 3. Then we add up everything in this product. So we are going to have minus 12 plus 2 plus 3. This is going to give us, that's going to be minus 12 plus 5. So the answer is minus 7. So a dot product of 421 and 313 is going to give us a multiplication of these two vectors, and then you add up everything in this plane. So we have minus 12 plus 2 plus 3, so giving us minus 7. Let's take one more example. Let's take one more example. Let's say we have another vector. Okay, let's do this. Let's do vector A times vector A. So vector A is what? Is minus 4. Is minus 4, 2, and 1, right? So we want to take vector A times vector A. So the dot product of vector A times vector A is going to look like this. Minus 4, 2, and 1, right? So this is going to be minus 4 times minus 4. That's going to be 16. 2 times 2 is going to be 4. And then 1 plus 1 is going to be 1. 1 times 1 is going to be 1. So the dot product of this is going to be 16 plus 4 plus 1. So this is going to be 21. So this is the dot product of vector A by vector A. I hope this makes a lot of sense, right? So that's all for dot products. The next is going to be cross product, which is a little more complex. So let me start all over again. So the next, we're looking at vector cross product. Which is a little bit more complex. So look at it now. We have vector A times vector B. Remember I told you that a dot product is represented by a dot, but a cross product is represented by a cross. So they are not the same thing, right? So it's going to give us vector C, obviously. So let's say we have vector 2, 3, 4 for vector A, vector 2, 3, 4 for vector A, and then vector 5, 6, 7 for vector B. So what's going to be a cross product of this? What's it going to look like? I'm going to give you a formula for finding the cross products because it's very complicated. So what we do is in this case is that, right, we ignore what is in this first plane. So this is x, y, z. So we ignore what is in the x, y, in the x plane, and then we figure out this remaining matrix. So this is a matrix now. So we figure out 3, 4, 6, and 7, right? So we say 3 times 7 equals to 21, and then 4 times 6, and then 4 times 6 equals to 24. So we have 21 minus 24 for this plane, which is equals to minus 3. Right? Then next thing, we do the same thing. We have 2, 3, 4. Around this mouse. 2, 3, 4. Then 5, 6, 7. Right? So we take out this plane, the second plane, the y plane. We take it out. Then we solve for 2547, right? So we go this way first. You know, the first time we went 3 times 7 minus 4 times 6. This time around, we are going this way first. So we are doing 4 times 5, which is 20, minus 2 times 7, which is 14. This is going to give us 6. Right? So we are going to do for the third plane as well. So this is 2.
No, I think it's 2 times 7 minus 4 times 5.
You said what?
Is it not 2 times 7 minus 4 times 5?
No, it's 4 times 5. Don't worry, I would explain. I'm just using this to give you a formula anyways. It's 4 times 5 minus 2 times 7. So the second one is 2, 3, 4. Right? And this is 5, 6, 7. So we're going to take out this third plane now. And we're going to solve for this remaining. So this is going to be so here we had a falling diagonal. We had a falling diagonal minus a rising diagonal. This is the formula. It's first the falling diagonal minus the rising diagonal. In the middle, we have a rising diagonal minus a falling diagonal. That's why it was first 4 times 5 minus 2 times 7. Lastly, we have a falling diagonal once again minus a rising diagonal. So this is 2 times 6. So this is a falling diagonal first. 2 times 6 is 12 minus 5 times 3, 15. So this is going to be minus 3, right? So our cross product of A and B is going to be 3 minus, is going to be minus 3, 6 minus 3. So our final answer is minus 3, 6, minus 3. Which if we are going to simplify, is going to be 3 into minus 1, 2, minus 1. Does that make any sense? So this is the cross product. If you remember, the dot product gave us a scalar quantity, right? But the cross product is going to give us a vector. Does this make any sense? Or I should take another example. Should I take another example? Hello, is anyone there?
Yes.
Okay, let me take another example. And then I'm going to give you a classwork that you're going to do for me before I move into the next. So let's say vector A is 1, 3, 2. And then vector B, this is a cross product, don't forget, cross. And then vector B is 4, 1, 8. So give me the cross product for this. So we're going to take the first plane and solve for the remaining 2 planes. Don't forget, it's first the falling diagonal minus the rising diagonal. So this is 3 times 8, 24, minus 2 times 1, 2. So the first is 22. So now let's take out this. Take out 3, 1 and solve for this. For this time is rising diagonal first. That's 2 times 4. 4 minus 1 times 8, which is 8. So this is going to be minus 4. So this is going to be minus 4. And then lastly, we're taking 2, 8 out, and they are solving for this. Lastly, this is falling diagonal first. That's 1 times 1, 1. Minus 3 times 4. That's 12. So we have minus 11. So our
Sorry,
cross,
2 times 4 is 8. Not 4.
where is that?
It's the second one.
The second one, we had 1 times 8, which is
2 times 4 minus 1 times 8.
2 times 4, which is
Yeah.
8, and then 1 times 8.
That's
Yes, thank you. Thank you.
That's
Thank you. Okay. So we have 8 minus 8. That's 0. So this is 0. And then 1 times 1 minus 3 times 4. So this is minus 11. So we have 22, 0 minus 11. Again, we can take out 11 from here. It's going to give us 2, 0 minus 1. So let me give you a classwork now. Right? Give me the cross product of 3, 2 minus 4 times itself. 3, 2 minus 4. Go. What did you get? Cross product of 3, 2 minus 4 times 3, 2 minus 4. Using the same formula. Don't forget, the first one is going to be a falling diagonal first minus a rising diagonal. The second one is going to be rising diagonal minus falling diagonal, while the third one is falling minus rising diagonal. So write down the formula and then give me the cross product of 3, 2 minus 4 times 3, 2 minus 4. You have 2 minutes. 2 minutes is not too much, safe.
Zero, zero, zero.
Okay, that's your answer. Who else? Who else? Who else is in? Chineye, what did you get? Essie, what did you get?
Zero, zero, zero.
Okay. Who else? Last person, what did you get? Who else? So I'm waiting for one more person. So 000 is correct. Because of time, I'm not going to go over it. Right. So we're just going to the next. I still have time though. Let me see. So the next is matrix vector multiplication. You see why matrix vector multiplication is important by the time we going to Monday's class. Although Monday's class, I think I will record it because I have a meeting in Lagos on Monday morning. So matrix vector multiplication. Who is there? Matrix vector multiplication. So let's say we have a matrix 1, 4, 2. Then we have a 2 by 3 matrix like this, or 3 by 2 matrix like this. 0, 1. This is a matrix. Once multiplied by vector 1, 5. How do we do this? Any idea? Any idea? So what we do is just like what we did in the last topic. Hey, my battery. All right. So what we do is we take what we have in this first plane, we multiply it by 1 and 5. Then we take what is in the second plane, we multiply it by 1 and 5. Then we take what is in the third plane, multiply it by 1 and 5. So let's do that. So this is going to give us 1 times 1, 1 times 1 plus 3 times 5. So then we take 4 zeros. So 4 times 1, 4 times 1 plus 0 times 5. I mean, this is very simple. So I'll take only one example because of time. Then we have 2 times 1. 2 times 1 plus 1 times 5. So this is going to give us 1 plus 15, that's 16. 4 plus 0, that's 4. Then 2 plus 5, that's 7. See, the wisdom here is that this is a 3 by 2 matrix. This is a 3 by 2 matrix. Multiplied by a 2 by 1 matrix. So a 2 by 1 vector, giving us what? So we take out this 2. Let's give us a 3 by 1 vector. You see that matrix vector multiplication always follows this rule. If you have an 8 by 3 matrix and you multiply it by a 3 by 1 vector, you'll find that this 3 will cancel this 3, and then your result is going to give you an 8 by 1 vector. But because this is so simple, we're going to move on to the next topic, right? Which is matrix multiplication. I hope you are writing this thing down in the book because we are building up to something. We are cooking to a point. And at the end of this month, okay, we have one more week in January. At the end of the first week in February, we would have been at the end of linear regression, and all this nonsense that we are doing will now start to make sense. So let's do matrix multiplication now. So let's say we have matrix 1, and this one is so simple too. We are going to do only one example. So let's say we have matrix 1, 4. We have 3, 0, and then we have 2, 1. 2, 1, right? So this is a decent 2 by 3 matrix. So this is a 2 by 3 matrix. We want to multiply this by another matrix. 1, 1, 0, 5 by matrix 3, matrix 3, 1, 2. So how do we do this now? This is a 3 by 2 matrix. Obviously, like I explained, this is going to give us a this 2 will cancel this 2, this 3. We're going to have a 2 by 2 matrix. But how do we do this now? So we take this first plane. So we take matrix 1, 3, 2. Sorry about my handwriting. 4, 0, 1. Right? We multiply it by this first plane, 1, 0, 5. So 1, 0, 5. Then we take the same matrix. Four, 0, 1. Then multiply it by the second plane. I've taught you how to do this in the previous class, the matrix vector. So you are going to have to do this for me. So this is matrix 3, 1, 2. So what's this first plane going to give me? I'm waiting for the answer. Then what's second plane going to give me? You have 1 minute. So you just basically do 1 times 1 plus 3 times 0 plus 2 times 5. Then do the second one. So quickly give me the answer. Anyone? Has anyone gotten the answer? Okay, it has ended. All right.